Okay, class, we're going to talk about chapter 14, the citric acid cycle. A few things that, looking at the citric acid cycle, it really follows after glycolysis. So, what we're going to do is we're going to learn a lot from glycolysis, looking at the substrates, products, chemical reactions for each step. Now, one thing we're going to look at is looking at what key concepts that we're going to pull from this chapter. So, one of the key concepts we got to look at is pyruvate dehydrogenase complex got three types of enzymes that collectively remove a carboxylic group from pyruvate and produce acetyl-CoA and NADH. Now, when we look at that, what is used is basically what we call the reaction. So let's take a look at it. You got pyruvate plus CoA plus NAD plus yields acetyl-CoA plus carbon dioxide plus NAD plus. So here you see in this figure is the model of the E2 core of the pyruvate dehydrogenase complex. So A has the azotobacter valiante complex. You got 24 E2 polypeptides. They are arranged in a cube. And then in B, what you see is the 60 subunits of the E2 core stereothermophilus forms a dodecahedron, a shape with, they say, 12 pentagonal faces. So that's what you see there. Now, moving on, pyruvate dehydrogenase complex works in 5 steps. Now, these 5 steps you need to know for your exam. So, the first step, E1 decarboxylate pyruvate, the C2 CO2 is released. So that's what happens. So in the first step, which is catalyzed by E1, this reaction requires the cofactor thiamine pyrophosphate, and that's TPP. And TPP attacks the carbonyl of the pyruvate, and the departure of CO2 leave the hydroxyethyl group attached to TPP. Basically, this carbocation is stabilized by the positive charge thiazolonium ring group of TPP. And then step 2, a leftover hydroxyl group is transferred to E2. And then the acetyl group is then transferred to CoA. Step 4, E2 is restored. And then step 5, E3 is restored to NADH. So let's go through this step by step. So thiamine is vitamin B1. And it's a cofactor for several decarboxylation reactions. So this is what you see here. So going through it, this step 1 on the decarboxylation of the pyruvate. And that's what I mentioned earlier. This reaction requires the cofactor TPP. And that's what happens, and you get that hydroxyethyl group TPP. And then that carbocation is stabilizes that. Okay, so I already talked you through step 1. Step 2, E2 uses a lipoamine cofactor. So the hydroxy group is transferred to E2. The hydroxyl acceptor is a lipoamine prosthetic group. And so that's what it is. So that's what you see, the liponic acid, and you see that there. And this prosthetic group consists of liponic acid via an amine bond to the amino group of a protein lysine residue. The active portion of the 14 angstrom long lipoamine is the disulfide bond, and that's in red, which can be reversibly reduced. So that's step 2 right there, is getting transferred The transfer regenerates the TPP cofactor of E1 and oxidizes the hydroethyl group to an acetyl group. Okay, so that's what happened in step 2. Now in step 3, E2 transferred the acetyl group to coenzyme A, producing acetyl-CoA and leaving the reduced lipoamine group. So that's what you see there. Now recall that acetyl-CoA is a thioester, a form of energy currency. Some of the free energy released from the oxidation of the hydroethyl group to an acetyl group is conserved in the formation of acetyl-CoA. And then step 4 is the restoration of E2. Now these are the final, step 4 and 5 are the final steps of the reaction restore of the pyruvate dehydrogenase complex to its original state. Okay. E3 reoxidizes the lipoamine group of the E2 by transferring electrons to a cis-cis disulfide group in the enzyme. So that's what you see there. It uses the disulfide bond and a FAD cofactor, and the lipoamine is oxidized by E3's disulfide. Okay, so when you do that, in step 5, the electrons move from FDA to FADH2. The electrons move from FDH2 to NAD plus to form NADH and H plus, and then E3 is restored to its oxidized state. So that is what's going on. And during the 5-step reaction, the long lipoamine of E group acts as a swinging arm. That's what it's doing. And visit the active sites of E1, E2, and E3 with the multi-enzyme complex. This arm picks up the acetyl group from E1 subunit and transfers it to the coenzyme A in the E2 active site. The arm then swings to the E3 site where it's reoxidized. Some other multi-enzyme complexes also include swinging arms, often attached to a hinge protein domains to maximize their mobility. Okay, what you see here is basically the summary of the pyruvate dehydrogenase reaction. So this is all of it together and how it looked. Like I said before, this would be a major part of your final exam. Your final exam is a standardized version of the test. So you will see this again. Make sure you understand and you know everything about this reaction, how everything is broken down. One thing I want to say, a multi-enzyme complex such as the pyruvate dehydrogenase complex can carry out multi-step reactions because of the product of one reaction can become the substrate for the next reaction without diffusion away or reacting with another substance. So that is what the multi-enzyme complex is. So make sure you understand and know that. Now, there are key concepts in 14.2 that you need to know. Now, what we're going to do is go over the 8 reactions of the citric acid cycle. The citric acid cycle is very important. So you need to know set of 8 reactions in which the acetyl group is condensed with oxalo acetate, 2 carbon dioxides are lost, and the oxalo acetate is regenerated. Each round of the citric acid cycle produces 3 NADH, 1 QH2, and 1 GTP or ATP. Now, when flux goes through the citric acid cycle, is regulated primarily by feedback inhibition at 3 steps. The citric acid cycle also likely involved by the combination of oxidative and reductive pathways. So redox reactions. So redox reactions are very important when it comes to this. Now, what you see here in the picture is basically the reactions of the citric acid cycle. And what we're going to do is go through that in general. So we're going to start with reaction 1 and go from there. Now with reaction 1, the acetyl group of acetyl-CoA condenses with the 4-carbon compound oxaloacetate to produce a 6-carbon citrate. So that is what you see here. Now, with that citrate synthase, it undergoes a conformational change upon binding the oxaloacetate. That's allowed for binding of the acetyl-CoA. Now, in A, what happened is the enzyme is absence of the substrates. 2 subunits of the dimeric enzyme are colored in blue and green. So that's what you see in A. In B, when the oxaloacetate is red, it's buried in there, binds, each subunits undergo a conformational change that creates the binding site for acetyl-CoA. An acetyl-CoA analog is shown in orange. That's what you see there. This conformational change explains why oxaloacetate must bind to the enzyme before acetyl-CoA can bind. Okay, with that, citrate synthase is one of the few enzymes that can synthesize a carbon-carbon bond without a metal ion cofactor. Now, let's take a look at the mechanism of citrate synthase. And so this is what you see here. So first the oxaloacetate and then the the acetyl-CoA bind to the enzyme. So that's what you see there. Now, in the next part 2, you see AsP375 is a base, removes a proton from the acetyl group to produce an enolate, which is stabilized by a hydrogen bond to HIS-274. This is the slowest, or as you remember, rate limiting step of the reaction. And then in part 3, the enolate attacks the oxaloacetate to produce a citral-CoA intermediate. So that's what happens in step 3. So that's what you see. That's what you see actually going on. Now, with that, you got another part of this mechanism. You got hydrolysis is releases the CoA and the citrate. So that's what goes on there. What is all of this? Thinking back to organic, and for those of you who are inorganic now, what you are seeing is basically redox reaction. What everybody got to think of, you're going to have redox reaction, especially when you have glycolysis in the body, because you are dealing mostly with water, and water has hydrogen in it. And so you're going to see a lot of proteination that is going on. So this is what you're technically seeing here. Now, let's move on to reaction 2 in this cycle. Now, with reaction 2, aconitase isomerizes citrate to isocitrate. And so that's what it is. And so you have the second enzyme of the citric acid cycle catalyzes the reversible isomerization of citrate to isocitrate. Now, the enzyme is named after the reaction intermediate. Now, citrate is a symmetrical molecule, yet one of only of its 2 carboxy methyl arms undergoes dehydration and rehydration during this reaction. The stereochemical specificity long puzzled biochemists, so they've been really puzzled by this. Han Krebs, who described the Krebs cycle, the citric acid cycle, or the Krebs cycle. Alexander Ockstrom pointed out that although the citrate is symmetrical, the 2 carboxy methyl groups are no longer identical when it is bind to an asymmetrical enzyme. So that's what happens. So stereochemistry in this case actually plays a part. Okay, let's move on to reaction 3 in the citric acid cycle. Now, the isocitrate dehydrogenase releases the first carbon dioxide. So that's what happens here. So it's an oxidated decarboxylation reaction. So that's what happened here. The substrate is first oxidized in a reaction accompanied by the reduction of NAD plus to NADH. Then the carboxylic group beta to the ketone function, that is the 2 carbon atoms away from the ketone, is eliminated as CO2. Then you got a manganese ion in the active site, helps stabilizes the negative charges of the reaction. So that is what happens there in step 3. Now, keep in mind that the CO2 molecule generated by the isonitrate dehydrogenase, along with CO2 generated in the following reactions, and the CO2 produces decarboxylation of pyruvate. It's diffused out of the cell and carried into the bloodstream of the lungs, where they are breathed out. Note that these CO2 molecules are produced through redox reactions. The carbons are oxidized while the NAD plus is reduced. O2 is not directly involved in this process. Okay, what happened in step 4? Alpha ketoglucarate dehydrogenase releases that second CO2. That's what happens there. It catalyzes an oxidative decarboxylation reaction. It also transfers the remaining 4 carbon fragments to the CoA. The free energy of oxidizing the alpha ketoglucarate is conserved in the formation of the thioester succinyl's CoA. Now, looking at this is a multi-enzyme complex that resembles the pyruvate dehydrogenase complex in both structure and enzymatic reaction mechanism. In fact, the same E3 enzyme is a member of both complexes. All right. So when we talk about that, look at the fates in there. The 2 carbon released the first round of citric acid cycle did not come from coacetyl A. So that's what you're seeing going on. So we're going through the first steps. So now what's going on? Let's look at reaction 5. So succinyl-CoA synthetase catalyzes substrate level phosphorylation. Okay, so this is a thioester and it has a large amount of free energy. So when it has a large amount of free energy, it releases that, and with that large amount of free energy, the net reaction is near zero. So this reaction can be, in some cases, reversible. And so what you see here is basically that. So how does it couple with the thioester cleavage of the synthesis? The reaction is a series of phosphoryl group transfers that have active site histidine residue. The phosphor-his reaction intermediate must move a large distance to shuttle the phosphoryl groups between the succinyl group and the nucleoside diphosphate. Okay. The succinate dehydrogenase generates ubiquinol. Okay, now do you see where ubiquinol is coming into play? Okay, so this is a part of the final 3 reactions converts the succinate back to its cycle starting substrate oxaloacetate. It catalyzes. So this is what you see here. And so if we go back, is basically what you see here. Now, what they're saying is to regenerate the enzyme, the FADH2 group must be reoxidized. Since the succinate dehydrogenase is embedded in the inner mitochondrial membrane. It's only 1 of 8 central cycle enzyme that is not soluble in a mitochondrial matrix. It can be reoxidized by the lipid soluble electron carrier ubiquinone. So, rather than have the soluble cofactor, ubiquinone acquires 2 electrons to become ubiquinol, which is QH2. So ubiquinone is Q, and then it needs those 2 electrons to become ubiquinol, which is QH2. So that is what's going on there, and that's what you see at the bottom. Okay, now reaction 7, the fumarase catalyzes the reversible hydration of a double bond to convert fumarase to malate. And so that's what is going on right here. So that's the 7 reaction, plain and simple. Reaction number 8, the malate dehydrogenase regenerates the oxaloacetate. So we back to where we started. So that is what goes on. We're back. So what happens in this reaction? The NAD plus dependent oxidation reaction. The standard free energy of change for this reaction is a plus 27.9 kilojoule per mole, indicating that it has a low probability of occurring as written. However, the product is a substrate for the next reaction. This is highly energonic and therefore highly favorable. Citrate synthase reaction help pull the malase dehydrogenase reaction forward. This is the reason for the apparent waste of energy released by cleaving the thioester bond of acetyl-CoA in the first reaction of the citric acid cycle. Okay, so this is the citric acid cycle, and this is an energy generating cycle. That's what we want you guys to really understand. Each NADH yields approximately 2.5 ATP, and each ubiquinol yields approximately 1.5 ATP. There, and what basically happened, every acetyl unit that entered the acetic acid can therefore generate a total of 10 ATP equivalents. The energy yields of a molecule of glucose, which generate 2 acetyl units, can be calculated. Now, when you go through all of this and you look at all of this, this is called the Pasteur effects. It is named after Louis Pasteur, which are first observed in the glucose consumption by yeast cells that decreased drastically when cells were shifted from anaerobic to aerobic growth conditions. Okay, so with that being said, now the citric acid cycle is regulated at 3 steps. Flux through the citric acid cycle is regulated primarily at the cycle's 3 irreversible steps. Those catalyzed by citrate synthase, reaction 1, reaction 3, the isocitrate dehydrogenase, and then reaction 4, the alpha glucarate dehydrogenase. Those are the major regulators. Step 1, step 3, and step 4. Please remember that. Step 1, step 3, and step 4 are the ones. Inhibition is represented by the red symbols, activation by the green symbols. Okay, the citric acid cycle supplies precursors for the synthesis of other compounds. Now, when going through this, the other thing that you got to make note of is the citric acid cycle intermediates can be replenished as well. So, let's take a look at that. Now, let's look at an example of this amino acid formation from this cycle. Now, how when we do this. Now, what you have here is basically an example of the amino acid. Now, what can happen here? So you can have that alpha gluconate, glucamate, dehydrogenase, and then you can get your glucamate there. So that's one of them that can actually happen. Now, the glucamate is a precursor to all of that, and so this is just an example of that. Now, let's talk about the citrate transport system. Now, both citrate and pyruvate crosses the inner mitochondrial membrane via specific transport proteins. When it do that, the system allows the carbon atoms from the mitochondrial acetyl-CoA to be transferred to cytosol for the synthesis of fatty acids and cholesterol. See, there's another reason there. The citrate transport system. You can actually see that and use that for transporting different systems. Now, what can happen to these intermediates? Now, these other intermediates can be diverted to other pathways and then can be replenished. So that's what can happen. So the amino acids, they can go to different other places and be replenished. So what can happen? So let's look at the anaplastoric reactions that replenish the citric acid cycles. So here you got pyruvate plus CO2 plus ADP plus water give you the oxaloacetate plus ADP and P sub I. So you see this, and you can get aspartate, pyruvate, and you can get all of that. So that's what you see here. Now, on the other hand, you can have this, where doing exercise, some pyruvate can be converted to alpha-ketoglutarate to boost the activity of the citric acid cycle. So you can have that can happen as well. Now, what other things what I want you to know from this chapter? In order for pyruvate, the product of glycolysis, to enter the citric acid cycle, it must undergo oxidative decarboxylation catalyzed by multi-enzyme pyruvate dehydrogenase complex, which yields acetyl-CoA, CO2, and NAD+.